Okay, we're back, and this is the second part of the lecture on cost-benefit analysis, dealing with uncertainty in cost-benefit analysis. And we left off on the topic of risk aversion. So we will now talk about risk aversion and then certainty equivalence, which is a way that we sort of compare two different risky courses of action, or one risky, one unrisky. So let's think about risk aversion. And to motivate risk aversion and why we believe in risk aversion and why risk aversion is present, I'm going to present to you a classic paradox. It's called the St. Petersburg Paradox. And the idea is the following. Consider the following coin toss game. A fair coin, and that's what we always say, fair coin if it's a 50-50 coin, not a biased coin, is tossed repeatedly until a tail appears. So you just keep tossing it until a tail appears. You could be heads, heads, tails, heads, 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 tails, or you could get tails in the first flip, whatever. But the pot of winnings starts at $2. The pot is doubled every time a heads appears. And you win whatever is in the pot when the first tail appears. Okay? So it keeps doubling from 2 to 4 to 8 to 16 to $32 in the pot. As long as you keep flipping heads, the pot doubles. And when you get your first tail, that's when the game ends and you get whatever's in the pot. The question is, what would you pay to play this game? What is it worth to you to play this game? And think about it. Before we move to the next slide, before you look at the next slide, take a moment and think. Any idea what it might be worth to you to play this game? How much you'd be willing to pay? Well, let's think about the expected value, right? What's the value of playing this game? On average, if you played this game, many, many times, what would be your average winnings from playing this game? Well, to do expected value, of course, we have to do, it's a combination of, it's a weighted product of values and probabilities. So we got to figure out the probabilities. What's the probability of the first tail being on toss 1? Right. And it's 1/2. What's the probability of the first tail being on toss 2? Well, it's that you get a heads on the first toss and a tail on the second. So there's 1/2 time you'll get heads in the first toss, and 1/2 you'll get a time you'll get a tails in the second. So it's 1/2 times 1/2, or 1/4. And so the probability of the first tail being on toss n, whatever it is, toss 4, toss 5, toss 20, toss 100, is 1/2 to the n. Right? So for example, the odds of it being on the third toss is 1/2 times 1/2 times 1/2, or 1/2 to the third, or 1/8. All right. So with those probabilities in mind, remember that you start off at $2 no matter what. You have $2. And if your first flip is a tail, then that's all you get. But if it's a heads, you keep going. And you keep going as long as you keep getting heads. So what's the expected value? Well, there are an infinite number of values, because theoretically you could, even if it's a 50-50 chance, you could flip, continue to flip heads forever, or at least 1,000,000 heads in a row. It's possible, unlikely, but it's possible. And so let's associate the different values you could win with the probabilities. Well, you could win $2. As we said, that's when the first tail is on toss 1. You could win $4. You could win 8. You could win 16. You could win 32. You could win every different multiple of 2. And not multiple of 2, every power of 2. 2, 2 squared, 2 cubed, 2 to the 4th. Those are all the possible winnings. And the associated probabilities, the probability to win $2 is 1/2. The probability to win $4 is 1/4. The probability you win $8 is 1/8. And the probability you win $16 is 1/16, and so on. So if you sum this up, the expected value is $1, 2 times 1/2, $1, 4 times 1/4, 8 times 1/8. Every single occurrence is $1. So expected value is $1 plus $1 plus $1 plus $1 out to infinity. The expected value of this game is infinite. So, back to the question. What would you pay to play this game? Would you pay an infinite amount? That's what it's worth. That's the expected value. Would you pay $1 million to play this game? Would you pay $1,000? Right? Unless you are willing to give every penny you own to play this game, then you are risk averse. Right? Because if you're not risk averse, if you're risk neutral, as we'll explain in the next slide, that means that you would be willing to pay the certainty equivalent, or you'd be willing to pay the expected value, which is infinity. You certainly would be willing to pay $1 million, at the very least, to play this game, even if you were a little risk averse. Of course, most people will say, well, geez, I could just win $2 50% of the time. I could win 4. I could maybe get lucky and win 8. And most people, wouldn't pay more than $10 to play this game, even though the expected value is actually infinite. So that suggests to you that people are risk averse, that people are, at least in certain situations, not willing to. They don't value a uncertain gamble at its expected value. They value it, particularly when we're talking about in gains, they value it as less than its expected value. What it's worth to them is less than the expected value. So consider here now an easier coin flip game. Suppose we simply flip a coin once. And if it's heads, you get $1 million. If it's tails, you get $0. Right? I flip a coin. If you get heads, it's $1 million. Tails, you get nothing. Now, the question, what would you pay to play this game? Assume you had no budget constraint. You could spend whatever. You could finance the money or whatever. You could borrow it. But you could, what would it be worth to you to play this game? Now, the expected value, of course, is 1/2 times $1 million plus 1/2 times 0. The expected value is 500,000. And so what would you pay to play this? Another way to look at this, an alternate question, is what amount would you have to receive with certainty in order to prefer the certain pay after the coin toss? So if I offered you, I presume if I offered you $1 million for certain, or the coin toss, you certainly should take the $1 million. If I offered you 800,000, 500,000, 400,000, 300,000, how much, what's the minimum amount you would have to receive with certainty, no gamble, in order to prefer the certain payoff to the coin toss? Again, think about that before looking at the next slide. So think for a second. If you were told you could either flip a coin, and if it's heads, you get $1 million, tails, you get 0. What could I offer you? What's the minimum I could offer you with certainty to have you choose my offer over the gamble? I presume if I offer you $10, you'd rather flip a coin. I presume for most people, if I offered you $800,000, you'd rather take the money than take the risk. But think about it. What would you, if I offered you $200,000, would you do it? $300,000, $400,000? Would you take that for certain rather than prefer that over the coin toss? Well, the expected value, as I sort of already said, right, is 500,000, right? So 50% chance of $1 million, 50% chance of 0. 1 million times 1/2 plus 0 times 1/2 equals 500,000. So the expected value of that coin flip game is 500,000. So if you go back to the alternate question, what amount would you have to receive with certainty in order to prefer the certain payoff to the coin toss? If I offered you 500,000, would you rather have the certain 500,000 than the gamble with the expected value of 500,000? Most people, I would imagine, would say yes. But what about 400,000? What if your choice, 500,000 is off the table? What if your choice between 400,000 guaranteed or the coin flip? Would you take the 400,000? Or about 300,000? What amount would be the minimum that you would have to be offered with certainty for you to prefer that over the coin flip? Now, if you are risk neutral, and we'll define those terms in a second, but that basically, you're immune to risk. You only care about the expected value. To you, something that has a value of 500,000 is the same as something that has a certain value of 500,000. Then your answer to that question would be 500,000. You would have to receive at least 500,000 in order for you to prefer that to the coin flip. But if your answer to the question, when you ask the question, what amount would you have to receive with certainty in order to prefer the certain payoff to the coin toss? If your answer is anything less than 500,000, then you are risk averse. Right? And most people are indeed risk averse. at least in gains. We talked about last class about loss aversion, how people are risk seeking in losses. So what are these terms that we're throwing out there? So a risk neutral decision maker focuses only on expected value. Does not care about the probability distribution which produces that expected value, right? If one thing is highly risky, one thing is less risky, but they both have the same expected value, to the risk neutral decision maker, they're the same. A risk-averse decision maker does care about expected value, right? More is better, but also seeks to minimize the risk, right? So in other words, if there were two options, one, like I said, same expected value, but one was guaranteed and one was risky, they would prefer the guaranteed if they had the same expected value, right? And risk-averse decision makers tend to prefer probability distributions with lower variability in the possible outcomes. A risk-seeking or risk-taking decision maker cares about expected value but prefers higher risk, right? Prefers probability distribution with greater variability in the possible outcomes, right? That may seem unusual, but of course, there's gamblers and they prefer the risk sometimes. But also we saw in the last discussion about when we're talking about losses, when I've said to people, would you rather lose $500,000 guaranteed or would you rather lose $500 guaranteed or flip a coin and lose $1,000 if it's heads and lose nothing if it's tails? A lot of people, a majority of people, in fact, who surveyed, prefer the gamble. So people do behave risk-seeking or risk-taking behavior in the realm of losses. But usually, more generally, risk-averse, we think about things, particularly when we're evaluating, potential gains, certainly in terms of risk aversion. Now, generally, individuals, but also firms and public sector organizations are all generally risk averse. And this is not just a behavioral thing. It's not like we just, on a behavioral perspective, we're risk averse. I mean, it makes sense. You take a certain amount of gambles if you are a business, but you don't take, you are relatively risk averse because you worry about the downside if the gamble doesn't pay off. And so you do minimize your risk. We always think about having a risk premium in business, and that you've got to, if you want me to do something that's risky, I've got to see a return on my investment greater than what I would have to see on something that was less risky, right? And the same is true in the public sector as well, right? And this, by the way, is how insurance companies make money, right? Insurance companies, if everybody's risk averse, right, they can insure everybody because the idea there is if people are risk averse. And what happens is, in that case, I'd rather pay out a premium each month and avoid the risk of having this huge, loss of my home and my property and my car. And so I'd rather pay out that regular premium. And sometimes, I will get in the accident. I will, have a problem and the insurance company has to pay out. But if they do that among many, many people, right, they are getting the premiums from everybody and having to pay out only for some, and they can spread out their risk, and therefore they can make a profit. Because again, remember, because I'm risk averse, I'm willing to pay. For example, I'm willing to pay let's say I'll be willing to pay $200 to avoid a 10% chance of losing $1,000. Right? That's extremely risk averse. I mean, I'm pay $150 to avoid a 10% chance of losing $1,000. Well, if I do that, right, and you do that across multiple customers, right, each customer is paying a premium of $50, a risk premium of $50, and that's where the insurance company makes their money. So, how do we think about? Okay, so we say we're risk averse, but that doesn't really help us unless we can get a little more precise. And what I mean by that is, just saying that you prefer less risky options is difficult because by how much, right? What if we do a cost-benefit analysis and one of them has an expected value of 600, but it's risky, and one has an expected value of 500, but it's not risky. You have it for certain. Which do you choose? Well, one is a much higher expected value, but it has risk. How much do you adjust for risk? How much are you willing to sort of give up to avoid the risk? In this case, if you're not willing to give up $500, or if that's the expected value is I'm sorry, the expected value of the risky option is 600, but the value of the non-risky option, the certain option, is 500. Is it worth $100 in expected value for you to avoid the risk? Well, that depends on your utility function. And so let's think about what your utility function might look like if you're risk averse. And utility function is basically how happy you are with different levels of money, right? And think about it this way. Consider how happy you would be to receive $1 million, okay? For a moment, think about that. Think about $1 million and how happy you would be. Now, think about what if you had $2 million? Would you be twice as happy to receive $2 million? I'm sure you'd be happier with $2 million than $1 million, but would you be twice as happy? What if you received $10 million? Would you be 10 times happier with $10 million than $1 million? Or what if you received $1 billion? Would you be 1,000 times happier receiving $1 billion versus $1 million, right? Most people answer no to those questions. I mean, just from my own perspective, if I could get $1 million, it would take care of a lot of things, a lot of debt, a lot of issues, pay for my kids' colleges and things like that. Another $1 million would be great, but it wouldn't have as much of an impact on my life as that first $1 million. That first $1 million would have a huge impact. The second $1 million would have a positive impact on my life, but not the same. The third $1 million would even less. So each additional $1 million is good, but it doesn't, increase linearly. So therefore, what that says is that you have decreasing marginal utility of money, right? Doubling the money does not double the happiness, right? It increases the happiness, but it doesn't double it. So if you have decreasing marginal utility of money, each additional $1 million brings you less benefit. It brings you benefit, but it brings you a little less than the previous one. Similar to the idea of apples. Suppose you like apples. If I give you one apple, you might love it. If I give you two, you might like that. But eventually I'm going to be giving you apples. And that third apple, that fourth apple, that fifth apple, you're like, okay, I've had enough apples, right? The additional value of more apples goes down. And the same is true of money, right? So therefore, what that says, if you have decreasing marginal utility of money, right? Remember marginal thinking, the additional utility you get from an additional amount of money, then the utility of money is a concave function. What that means is it looks like this. Is that the utility, so we have money on the horizontal axis, or wealth, or whatever. So the money is on the horizontal axis, and the utility is on the vertical axis. So this is think of utility as sort of happiness, or benefit, or how good it is for you. Well, certainly you see, if you have $100, the utility is given here on the vertical axis where it intersects that curve. This is your utility curve. For your $500, this is the utility of $500 is given there, right? Notice, of course, that it's increasing, meaning the more money, the more utility, right? You could have $1 million, and having $1.1 million is at least a little bit better than having $1 million. It's always increasing, but it's increasing by a decreasing amount. So in particular, let's consider halfway between $100 and $500. So suppose you had $300, right? Notice that if you have $300, right, the utility going from $100 to $300 is this distance here. So when you add $200 to your wealth, your utility goes from this point where it says utility of 100 to this point where it says utility of 300. You add 200 more, you go up to the utility of 500, but that's not as big of a jump. Obviously, you gained more in utility by going from 100 to 300 and then from going from 300 to 500. The additional utility or happiness or benefit or quality of life improvement or whatever it is, that you consider utility, goes down as the money increases. And this helps explain, so far we haven't even really talked in this case about risk, right? This is just simply utility of money. But because people's utility of money tends to look like this, it helps explain risk aversion. So without uncertainty, so before we do that, and we'll go back to the graph to explain it, without any uncertainty, right? There's no uncertainty, everything is certain, then you maximize your utility. You choose whatever outcome will give you the maximum utility, right? And assuming, by the way, that if your utility is increasing in your wealth or money or net benefits, then maximizing net benefits will always maximize utility, right? And there's no uncertainty, so you don't have to worry about risk. It's just whatever maximizes your net benefits, because that's also going to maximize your utility. But once you have uncertainty, you maximize expected utility, right? because there might be, when you have risk or uncertainty, there might be multiple outcomes. Each outcome has a utility associated with it, right? Back here, for example, maybe you could potentially get $100, you could potentially get $500, you could potentially get $300, and with some probability, right? So the idea is that you don't know exactly what your utility is going to be because it's uncertainty, but you would maximize your expected utility, right? There's a 1/3 chance maybe you get utility of 100. There's a 1/3 chance you get utility of 300. 1/3 chance you get utility of 500. And so you maximize your expected utility. Now, if you're risk neutral, right? If you're risk neutral, then what that means, by the way, is that if you were risk neutral on this previous graph, your utility of wealth line would be straight. It would be going up in a, doesn't have to go 45 degrees, but a straight line to the upper right. That would be risk neutrality. And so if you're risk neutral, then anytime you maximize the expected payoff, the expected net benefit, expected wealth, expected dollar payoff, you're also maximizing expected utility. So the idea in that case, if you're risk neutral, if you have one option that has expected payoff of, or expected value of $600 and one expected value of $500, you'll always choose the one that has the value of $600. Even if the $500 is with certainty and $600 is very risky, you'll always choose whichever has the highest expected value. So for you, a risk neutral person, maximizing expected value, maximizing expected payoff is the same as maximizing expected utility. But for a risk-averse actor, maximizing expected dollar payoff is not equivalent to maximizing expected utility, right? For a risk-averse actor, a course of action with a lower expected dollar payoff may generate higher expected utility because it has lower risk. So to illustrate this, consider a gamble, a 50-50 gamble between $100 and $500. So suppose there's you have 50% chance you get 100, 50% chance you get 500. Right? What is the expected value? Right? In this case, the expected dollar value for that. Well, it's going to be a 1/2 chance of 100 plus 1/2 chance times 500, or 300. Right? That's the expected value of the gamble between 100 and 500. What is the expected utility? Right? Not the same expected value. What's the expected utility? Well, to do that, refer to our diagram that we had before. And so here we know that there is the expected value is 300, but we know that the gamble can either be 50% chance if it's 100, 50% chance it's 500. So in some sense, what we're doing is we're moving, between, you could draw a line, if you will. There's a couple ways to approach it. But you could draw a line between the point where $100 intersects the utility curve and where $500 intersects the utility curve, right? And the idea is that any gamble, right, a 50-50 gamble would have you sort of right in the middle of that line. A 60-40 gamble would have you, if there's a 60% chance of 500 and a 40% chance of 100, then you'd be closer to the 500 point. You'd be closer to up here. But what it means is that the weighted, because this is a weighted average. This line is sort of giving you the weighted average of utilities of 100 and 500 based on probabilities. And so it's a 50% chance of the gamble. What that means is that between the two, it means that we are going to end up, the expected value is 300, but expected utility is 1/2 times the utility of 100 plus 1/2 times the utility of 500, right? So we end up here, another way to look at it is simply, if this is the utility of 100, this is the utility of 500, then the expected utility of the gamble between the two is going to be halfway between those two utilities, which is, right there where the blue line is. That's the expected utility of 50-50 gamble. And the point is, notice that it is less than the utility of 300, right? The expected value is 300, but the expected utility is less than 300, or less than the utility of 300. So you would rather have $300 with certainty, because that gives you utility here, than have the gamble of 50-50 chance between 100 and 500. And that shows you how this utility function illustrates how a concave utility function helps explain risk aversion. Now, how do we treat uncertainty in cost-benefit analysis? Well, cost-benefit analysis usually rank courses of action based on net benefits. But when the costs incurred or the benefits accrue over time, as we discussed last week, the net benefits are the net present value, right? What's the, the net present value of those benefits. Under uncertainty, right? So instead of just having, at first we said, remember last week's lecture on cost benefit analysis over time, we simply talked about the idea that costs are incurred over time or benefits accrue over time. You have to adjust for inflation and discounting, but you still just calculate net present value. But what if not only are those costs and benefits accruing over time, they're also uncertain? You're not certain what they're going to be. They could be high or low or this. Well, then now you do expected net present value, right? Because your net benefits are the expected net present value. But that approach assumes a risk-neutral decision maker, right? If you just simply do expected value, that the cost could be, it could cost $1 million, it could cost $500,000, and with equal probability, therefore the expected cost is $750,000. Well, that is taking a risk-neutral approach. It's calculating expected net present value, but it's doing it in a risk-neutral approach. But often, the military or government often wants to avoid certain poor outcomes, right? You don't want to necessarily take particularly high risks in certain cases. You could have high risk, high reward. Sometimes you do want to take certain risks. But there's often a case in certain investments where you don't want to have the big failure, right? For example, if you're just playing around and you're DARPA and you can have a lot of failures, in some of your things, then that's one thing. But if you are developing a weapon system that really needs to be operational and effective in 4 years, you can't be too risky about it, right? You could, if you're choosing between two options, both of them risky, but one that could be a complete failure, but it could also be, game changing. Another that, could be excellent, but it could be not so good, but it's certainly not going to be a failure, but it has less risk associated with it. That may be preferable. And so the government often and military often are in situations where they have to be risk averse. Others they don't, but in many situations they do have to be risk averse. So in any cost benefit analysis, you'll have some courses of action that may have more uncertain net benefits than others. So how do you compare the two, right? How do you deal with the fact that, okay, you have two courses of action, they have different expected values. One may have a higher expected net present value, but it's risky. And one has a lower expected net present value, but it's not so risky. So how do you choose between the two? Well, again, if you have a risk-neutral decision maker, the expected net present value is appropriate the estimate. So that's fine. If they're risk-neutral, then you calculate expected net present value, right? You don't need to worry about things like utility functions and relative risk aversion, things like that. But when you have a risk-averse decision maker, more details about risk should be included in the cost-benefit analysis report, right? And we'll talk about how you can get great detail in the next section. We talk about certainty equivalence. But in particular, the guidance from the OMB Circular 894 about doing federal government CBA says, useful information in such report would include key sources of uncertainty, expected value estimates of outcomes, sensitivity of results to sources of uncertainty, and where possible, the probability distribution of benefits, costs, and net benefits, right? And this is so that you don't understand the expected value, but if you have the probability distribution, then the decision maker can do their own estimate of what the expected utility is based on their utility function, on how risk averse they are, right? You can adjust for risk aversion if you have this sort of information. So let's consider an example. Suppose we have in communication systems. Suppose there are 3 communication systems the Army is choosing among, and they differ, however, in how well they perform in different atmospheric conditions. System 1 is least affected by atmospheric conditions, but it is most cumbersome to use, so it yields a low benefit in normal times, right? So, if the weather conditions atmospheric conditions are normal, it does okay, but it does do much better than the alternatives when conditions aren't so good. System 2 can handle mild electrical storms, but does not fare well against severe storms. And finally, System 3 performs very well in normal conditions, but does not perform well in adverse conditions. So graphically, look at it like this. So these are a chart where the benefits of each of the different systems, System S1, S2, S3, as a function of the atmospheric conditions. So if the atmospheric conditions are normal, System 1 performs, you get the score, however it's scored, of 100. System 2, 120. System 3, 150. So under normal conditions, System 3 is the best option. Under mild conditions, System 1 does reasonably well, 80. System 2, 50. System 3, 10. So notice that system 1 is the worst performer in normal conditions, but we get to mild conditions, and it is clearly the best performer, and even more so under severe. In severe conditions, system 1 performs his rating of 50, system 2 rating of 20, system 3 nothing. System 3 can't function at all. So you see that what is the best system is really going to depend upon what you think the atmospheric conditions are going to be, what you project the atmospheric conditions to be. I mean, if they were always going to be normal, then you would choose system 3, right, 150. If you knew they would all be mild, right, you would mild, electrical storms, you would choose system 1, right? But depending on the probabilities of these different systems may affect, these different atmospheric conditions may affect what your best choice is. So suppose that the normal, mild, and severe conditions happen with 60%, 30%, and 10% probability respectively. So if you knew that, and that all three communication systems have the same costs, so we're doing a cost or benefit effectiveness analysis, right? Not a cost effectiveness analysis, a benefit effectiveness analysis. Which system would you recommend, right? Remember, benefit effectiveness analysis, everything has the same cost. We're trying to maximize a benefit for a given cost. Which system would you recommend? Well, so what we have, again, going back to this, we have the performance of each system under different atmospheric conditions. And now we have added here the probability of the three different possible atmospheric conditions. Well, that allows us to calculate expected value. So the expected value of the systems are, you take the value, which is the performance value, and for example, the first things here are on how they perform under normal conditions: 100, 120, 150, right? Going to the previous page, see 100, 120, 150. So what we did is take 100, 120, 150, each by 60, 80, 50, 10, each multiplied by 30, 50, 20, 0, each multiplied by 10. But we're summing it across for each system. So for system 1, they score 100 under normal conditions, which is 60% of the time, 80 under mild conditions, 30% of the time, 50 under severe conditions, 10% of the time. So they have a expected value of 89. Doing the same for the other twos, 120 times 60, 50 times 30, 20 times 10. Expected value of system 2 at 89. And finally, expected value of system 3 does 150 times 60% of the time. So when normal conditions, it is the clear star. 100 score of 150 under normal conditions, score of 10 under mild conditions, and score of 0 under severe conditions. And so it has the highest expected value. And so clearly system 3, for a risk neutral decision maker, would prefer system 3, right? Because on average, over the course of the year, over the course of, the time, if the conditions are 60% of the time are normal, 30% you have mild storms, 10% you have severe storms, you are going to get better performance on average over the course of time from system 3. But what if the Army is not risk neutral? Right? Notice that system 3 does great under normal conditions, but whenever you have mild storms or severe storms, you're not doing so good with system 3. What if the Army is not risk neutral? And you might think they shouldn't be, right? On the battlefield, it's pretty important to be able to maintain communications. You can't say, we bought system 3 because they had the high expected value, but we really, because of the storms, we really don't have very good performance. So it's great when there's normal conditions, but can we please call the enemy and tell them, hey, can we wait till tomorrow because we have severe, electrical storms today, so we really aren't capable of fighting today. Well, obviously you can't do that, right? So it's pretty important to be able to maintain communications, and so you want it to be robust against possible poor atmospheric conditions. So there's a sense that poor performance should be avoided, even if that's unlikely. Even most of the time you have normal conditions, and most of the time system 3 will outperform the others. You don't want to be in a situation where you have that poor performance under poor atmospheric conditions. So we must consider the shape of the Army's utility curve. Again, if the Army was risk neutral, the utility curve would be a straight line going up, a diagonal line. But the utility would increase linearly with the value of in this case, it's not money, right? It's the performance of the system. But if the utility curve is instead concave, so they're risk averse, right? We might get a different result. Well, how do we sort of mathematically, think about concave utility functions? Do we just draw them on a picture and draw lines? Well, you could. But we try to approximate them. We try to use a function to approximate them. And one common way of approximating risk-averse utility functions or utility curves is to have where the utility of some net benefits is net benefit raised to the power of z, right? And so in that sense, those curves, as long as z is less than 1, and I'll explain in a minute, those curves are going to be concave. If z is greater than 1, by the way, they'll be convex. You'll be risk-seeking. It'll curve up. But if the exponent z is less than 1, it'll be concave. So u here is the utility function. Net benefits, of course, are the NB is, of course, the net benefits. And Z is what we call the coefficient of risk aversion. And Z is something that reflects the attitude towards risk. If Z is equal to 1, then the Army is risk neutral, right? The utility of net benefits, if net benefits raised to the power of 1 is just net benefits, so the utility of net benefits equals net benefits. In that case, the Army is risk neutral, and they would choose system 3 in our example. But if Z is less than 1, then Army is the risk averse. And the lower Z is, the greater the risk aversion, right? So if Z is, 0.2, they're more risk averse than if Z is 0.8, right? And as we mentioned, sometimes for certain programs, you're going to be more risk averse than others, right? You're going to care about the downside risk much more in some than others. So it might not be that you always have Z being the same for the Army. Z is a standard, that Z has that the Army has a standard utility function with a standard coefficient of risk aversion, right? There have been studies that estimate the coefficient of risk aversion for people in general, but understand that it might vary for different programs. So if we say in this example the utility net benefits is equal to NB, the net benefits raised to the power of Z, how do we determine the value of Z? Right. Well, we could perhaps pick one level of Z and then try alternatives for sensitivity analysis. In other words, what you might do is, what if Z is 0.1? What if Z is 0.2? What if Z is 0.3? And if for most values of Z, you choose the same outcome, then it really doesn't matter how precise you are. One of the things I think I mentioned to you in the very first week in the lecture, the recorded lecture, was the approach on these assumptions is ready, aim, fire, aim again, fire again, aim again, fire again. And in particular, don't spend too much time on that initial assumption. So pick a Z that seems reasonable, run your analysis, get the conclusion, and then say, in your sensitivity analysis, what if you were wrong? What if Z was a little lower or is a little higher? Well, guess what? If it's a little lower and a little higher and it doesn't change your recommendation, then your conclusions are not very sensitive to that assumption. What I'm saying is there are a lot of assumptions that go into cost-benefit analysis. You want to devote your energy to those assumptions that matter. Because if you spent hours and hours and days trying to figure out the right Z, and in the end it turned out it didn't really matter. For most Z's, you're still going to choose option B no matter what. Well, then you wasted all that time. You didn't need to be that precise. So again, make an educated guess, run your analysis, then go back and do a sensitivity analysis and say, what if that is off? And then if you find it's very sensitive, if you find, well, wow, it matters a lot. If Z is a little bit lower, we choose a different option. If Z is a little bit higher, we choose a different option. If that happens, if you find that your results are very sensitive to Z, then go back and devote a lot of energy to figuring out what the right Z is. Right? So whenever you make assumptions, the first should sort of be quick and dirty assumptions, do the analysis, then figure out which assumptions matter, which assumptions, if changed, would change your results. And then those are the assumptions that you devote a lot of energy to making sure you get right. So how do we determine the value for Z? Like I said, the first way is perhaps pick one level of Z and then try alternatives. Another way is, if you've got a decision maker, you want to know how risk averse that decision maker is. You say, hey, boss, captain, or whoever it is, say to the colonel, sir, how much is 50% chance of $1 million worth to you, right? Give him the question we did. If you're going to flip a coin, and you can either get $0 or $1 million, or if you think about it, maybe not for himself personally, but say for this command, if this command could supplement its budget, and they could either, flip a coin and they would get, if it's heads, they got $1 million additional dollars on the budget of this office or this command, or if it was tails, they got no additional money. Or you could get $300,000 with certainty. Which would you take? $300,000 guaranteed, or flip the coin and potentially get $1 million more for this command? And if they says, well, I'll still take the gamble. You say, well, what about $400,000? What about $500,000? What about $450,000? And to figure out from that, you can then figure out, if he answers that question, then you can from that figure out how risk averse the decision maker is. And like I said, you may not want to phrase it as personally. They may be personally risk averse, or not so risk averse, but they might be more risk averse in their professional decisions. So you frame it in a professional way, that will get you some idea of what level of risk aversion you should use. Now, just for our illustrative purposes, let's take z equals 1/2, right? So let's say the utility of the net benefits is equal to net benefits raised to the power of 1/2, which is basically the square root, right? 10 to the 1/2 is the square root of 10, right? So anything to the 1/2 is the square root. So it's really saying the utility of the net benefits is the square root of the net benefits. Now, remember that a risk-averse decision maker maximizes expected utility, not expected value. Right? Now, expected utility is the weighted average of the utilities in each scenario. And the weights are, so remember, expected value is the weighted average of the values, right? The net benefit amounts in each scenario. The expected utility is the weighted average of the utilities of those net benefit amounts in each scenario. And the weights are the probability of each scenario. So in other words, in this example, when we're dealing with the example of the communication systems, the expected utility is going to be the probability of normal conditions times the utility under normal conditions, plus the probability of mild conditions times utility under mild conditions, plus the probability of severe conditions times utility under severe conditions. Right? Well, since the probability of normal is 60%, the probability of mild is 30%, the probability of severe is 10%, we can put those probabilities in there. We said that our utility function is net benefits raised to the 1/2, or the square root of the net benefits. So we just can plug in for the utility of normal under normal conditions is the net benefits under normal raised to the 1/2. The utility under mild conditions is the net benefits of that system under mild conditions raised to 1/2. And the utility under severe conditions is the net benefits under severe conditions raised to the power of 1/2. So, again, rewriting that up here on the top of this slide, then if we do that for all three systems, the utility of system 1, system 2, system 3, expected utility of system 1, system 2, system 3. I want you to contrast this. I'm going to quickly flip back to slides. Remember, we did this slide, we did the expected value up top, right? We did the net benefits, 100, 120, 150, 80, 50, 110. So these were the net benefits here, multiplied by the probability of those different outcomes. That was the expected value, where all we concerned about was maximizing expected net benefits. Well, now that we're risk averse, notice that we still take those probabilities of the different possible scenarios. 60% of the time it's normal, 30% of the time it's mild, and 10% of the time it's severe. But instead of multiplying just by the net benefits, we now multiply by the utility of the net benefits, which is net benefits raised to the 1/2, or the square root of the net benefits. So before, we didn't have these halves, right? If you eliminated all those halves, right, it would be exactly the same as before. But by adding the halves, right, we make this the square root of 100, which of course is 10, square root of 80, square root of 50, square root of 120. And if you calculate that, you do the math, the net benefits are as follows. The expected utility of the systems are as follows. The expected utility of system 1 is 9.39. Expected utility of system 2 is 9.14. Expected utility of system 3 is 8.30. So thus a risk-averse decision maker with a coefficient of risk aversion equal to 1/2 would choose system 1. Right? Remember before, without risk neutrality, we chose system 3, but system 3 now, under risk aversion, actually rates the lowest. Because basically, it does great under normal conditions, but when there are mild conditions, and especially severe conditions, it stinks. It really performs badly. So it is a big downside risk. And therefore, when you're risk averse, those are the sort of options that are going to score more poorly. That's the math. I'm a visual person, so let me walk through the same math, but let me walk through it with those charts. So remember this chart. This is not a new chart. So let's revisit our chart to provide some clarity here. This chart I showed you before. These are the benefits as a function of the system and atmospheric conditions, right? The benefits for each system, the net benefits of each system under each atmospheric condition, and the probability of those atmospheric conditions. So then, to calculate the utility, instead of benefits, all I've done is change it from benefits to utility. So now calculate the utility of each system under each atmospheric condition. We just take the net benefits and raise it to 1/2, or take the square root. So now all I've done is from the previous slide to this slide, the only thing I've changed is raised everything to the exponent of 1/2 to get the utility. Right? If we do the math, it then comes out like this, right? Those are the utilities. This is the utility of system 1 under normal is 10, the utility of system 1 under mild is 8.9, the utility of system 1 under severe is 7.1, etc. So now we have the utility as a function of the system and atmospheric conditions. Okay? All right. Well, now let's do the utility weighted by the probability. So for each of the utility, multiply it by the probability of that condition. So the probability of normal conditions is 60%, probability of mild conditions is 30%, probability of severe conditions is 10%. So I just multiply the utility of 10 times 60%, the utility of 8.9 times 30%, utility of 7.1 times 10%, right? And then we will get, if we do that, we get that in each cell. That's the utility weighted by probability in each cell there. Well, then the expected utility is simply sum across all scenarios. 6 plus 2.68 plus 0.71 is 9.39. 6.57 plus 2.12 plus 0.45 is 9.14. 7.35 plus 0.95 plus 0 is 8.3. Right? Notice, by the way, even under risk aversion, right, the system 3 significantly outperforms systems 1 and 2 under normal conditions, right? But it does, because of risk aversion, its score, is really pales in comparison to the others under mild or severe conditions. Well, and again, so that we choose the option with the highest expected utility, which is system 1, because of the expected utility of 9.39. So you see that the idea is that we looked at this choice of Army communication systems. When you use risk-neutral approach and expected values, we would choose system 3. But once you introduce risk aversion, which there always is, some presence of risk aversion, it's higher in some choices than others. It's understandable why we would be risk averse in this choice. We don't want a system that only works 60% of the time. It works very well 60% of the time, but 40% of the time it doesn't really work at all. You don't want that. So you've got to have some risk aversion. And so in doing so, we find that we end up choosing the system 1, not system 3, which we would have chosen if we just tried to maximize expected value. Now, one way, so that sort of introduced the idea of risk aversion. But notice that one thing that was convenient about this, for example, going back here, was that we had 3 systems, different utility under different atmospheric conditions, but the probabilities were all the same. So they all face a 60% chance of having normal, 30% chance of mild, 10% chance of severe. What if the probabilities are different? What if one of them, is always going to have a certain net benefit, and one of them is going to have a 3 possible net benefits, one has 2 possible net benefits? How do you, when it gets more complex, how do you sort of compare things? For example, one thing that is certain outcome with something that's risky, or 2 different risky outcomes, but the risks are different. In other words, one has a 30% chance of having this net benefit, a 35% chance of this net benefit, and 25% chance of this net benefit. The other one's a 50-50 of these 2 other net benefits. One of them has a guaranteed net benefit with no uncertainty. How would you compare those options? Well, the answer is we introduced this idea of certainty equivalence. And the guidance, so OMB Circular A94, which I gave you is the standard sort of broad federal government guidelines for how to do cost-benefit analysis. Under 9D, it says the following. In some cases, it may be possible to estimate certainty equivalence, which involve adjusting uncertain expected values to account for risk. Right? Well, if that's what they want me to do, I need to know one thing, which is, what is a certainty equivalent? Well, a certainty equivalent is the certain amount that is equally preferable to facing an uncertain outcome. So remember, let's go back to our coin flip, right? Where the easier coin flip, where a fair coin was tossed once, and if it gets heads, you get $1 million, and if it gets tails, you get $0. And I asked you the question, what amount would you have to receive with certainty in order to prefer the certain payoff to the coin toss? Right? What's sort of the minimum amount that you'd have to receive with certainty in order to prefer the certain payoff to the coin toss? Suppose you answer 400,000, which is reasonable, right? The expected value is 500,000. If you're risk averse, you're going to choose something less than that. You'd rather take 400,000 for sure than take the gamble. So suppose you answered 400,000, so that you would be, if somebody offered you 400,000 or anything above, that you would take that with certainty. But if they offered you something below 400,000, you'd rather take the gamble. So 400,000 for you is the threshold, that you would switch from preferring the gamble to preferring the certainty amount. Well, in that case, the game is worth a certain outcome of 400,000 to you, right? You would trade a certain outcome of 400,000 for this tossing the coin. So that's what the game is worth to you. Therefore, the 400,000 is the certainty equivalent of the coin flip game for you. So what we can do in that case, notice, so that way, if we wanted to compare two things, right, we figure out the certainty equivalent. Now there's supposed there's some other gamble. You know, you roll a die. If it's a 1 or a 2, you get 200,000. If it's a 3 or a 4, you get 600,000. If it's a 5 or a 6, you get 700,000. If you could figure out the certainty equivalent of that, you can compare the two. You know, you can compare these two different gambles. You can compare by figuring out what the certainty equivalent is of them, because you're putting them, remember from the very first day of class I talked about, you've got to, in order to compare costs and benefits and compare costs to each other and combine costs and combine benefits, you've got to be comparing apples to apples. You've got to put everything on the same scale. You can't really measure your costs in dollars and your benefits in customer satisfaction, right? Because you don't know, okay, well, is customer satisfaction worth a 10% improvement in customer satisfaction worth $1 million? I don't know. Or, you know, in a military context, what if we have a weapon system that's going to increase accuracy by 10%? Okay, well, increase accuracy by 10% and it costs $10 billion to do so. Is 10% more accuracy worth $10 billion? You've got to ultimately put things on the same, you know, yardstick. And certainty equivalent does that. It lets you take things that have different probabilities, different outcomes, different net benefits, different levels of uncertainty, and compare them all apples to apples by identifying the certainty equivalent of all the different courses of action. So note again, as I sort of mentioned, that the certainty equivalent in this case, 400,000, is less than the expected value because of risk aversion, right? And that's usually what you'll see. You know, usually the certainty equivalent for any gamble or uncertain outcome will be less than the value of that outcome. So again, certainty equivalent equals a certain amount that is equally preferable to facing an uncertain outcome. So the certainty equivalent has the same expected utility of the course of action. It's not the same expected value. Remember we saw before in the example, and I don't want to page back to the slides, but you know when we had the 50-50 gamble between $100 and $500, right? The expected utility, the expected value was $300. 50% chance of 100, 50% chance of 50, but the value is 300. But the expected utility of the gamble was less than the utility of $300. Right? So what you're trying to find is not the expected value of the uncertain outcome, but you're trying to find the value that yields the same expected utility of the course of action. And because of risk aversion, the certainty equivalence of an uncertain outcome is going to be less than the expected value. Right? You're going to want to be willing to take a value less than the expected value to get the same expected utility. So certainty equivalents allow us to compare courses of action with different levels of uncertainty on an equal basis. Right? Certainty equivalents give the net benefit amount or the net present value equivalent to a situation with no uncertainty. But computing certainty equivalents requires some knowledge or assumptions on the distribution of returns and the degrees of risk aversion. Right? So let me sort of explain it a little bit graphically, right, and how this works. So consider a course of action with two possible outcomes, right? There's two possible net benefit amounts, either A or B, right? And so here's our example, that there's some possibility that you could have a net benefit of A, which, again, the utility function is the utility of the net benefits. It's concave, which shows risk aversion. But if the outcome is A, you get this amount of utility A. And by the way, you might say, what are these measured in? It doesn't really, you know, utility isn't measured in dollars. It isn't measured in minutes. It's not measured in, it's measured in, sometimes people call it utils, right? It doesn't really matter. It's some mathematical measurement. You know, it doesn't really matter what the units are. Some mathematical measurement of utility. You know, you take something that's in dollars, you know, and because you have risk-averse utility, therefore it gives you a common measure. How can you measure things commonly? And you use utility as a common measuring stick, but it's not a measuring stick that sort of exists in a reality. It's a measure of happiness, right? I mean, how would you measure happiness? There's not a units of happiness per se. But so if you get outcome A, we'll achieve utility A there. You could get the outcome which yields net benefit B, and that would give you this level of utility, given by utility B, right? Those are the two possible outcomes of this course of action. Well, suppose there's a 60% chance of achieving net benefit B, and 40% chance of achieving the outcome with net benefit A. So 60%, instead of like a 50-50 flip, it's 60-40. So you're more likely to have B than A, right? Well, again, you're talking about any gamble is basically a weighted average of these 2 points, these two utilities. And so we could draw a line between the two of them, right? And 50-50 gamble, we would end up right in the middle of that line. If utility of A was more likely, we'd end up lower part of the line. Utility B was more likely. I'm sorry, if outcome B was more likely to end up closer. So a 60-40, and I don't know if I drew it that well, somewhere about there, right? So we would end up, with a 60% chance of getting B, 40% chance of getting A, we end up the expected value of the course of action, or the expected net benefits, is V. Like V equals 60% times B plus 40% times A. That's your expected value. Right? And if you actually receive that value, if somebody gave that to you, right, it would yield utility there. That's the utility of V, right? So you take the net benefit V, you find out where it intersects the utility curve, and go over here. That's the utility of V. That's the utility of the expected value, right? But that is not the utility of the gamble, right? Only if you were risk neutral. But we see because you were not risk neutral. In fact, right, the utility of the expected utility of the course of action is given by that point there, right? The idea is that, and you can either think about, because we end up at this point, and you go over from that point, what's the expected utility at that point? That's the expected utility of the course of action. Alternatively, you could have, for example, I don't necessarily need to draw that red dotted line, and sometimes I think it's confusing, particularly when you only have 2 outcomes, right? I could have just done that, if there's 60% chance of utility of B, 40% chance of utility A, then although again I'm not sure I drew it right, the expected utility, expected utility of the course of action should be 40% times utility of A plus 60% times utility of B, and so it therefore should be 60% of the way between those 2 points, right? Which it approximately is. All right, and so that's the expected utility of the course of action. This is the expected value of the course of action. This is the expected utility. And notice the expected utility of the course of action is below the utility of the expected value, right? That's due to risk aversion. If you're risk neutral, they would be the same. The utility of the expected value would be equal to the expected utility of the course of action. All right, well, so what is a certainty equivalent? Remember, a certainty equivalent is what certain outcome, certain net benefit value, yields the same utility as your course of action. Has a utility equal to the expected utility of the course of action. So what certain outcome gets the same utility as the expected utility of the course of action? Well, if we go over here and we see, look at the utility curve, the point on the utility curve that generates exactly that utility, in other words, the net benefit that generates exactly that utility is given right there, right? Where the expected utility, where this level, that's the point on the net utility curve that generates a utility exactly equal to the expected utility of the course of action. Well, what does that mean in terms of net benefit? Well, what that means is that if we draw the line down here, so a net benefit of C with certainty gives you a utility which is exactly equal to the expected utility of the course of action, right? The utility of C is equal to the expected utility of the course of action. We don't say expected utility of C because it's certain. There's no uncertainty there. So guaranteed benefit of C is exactly equal to, in terms of value or in terms of utility, to the gamble between A and B, right? And therefore we call C the certainty equivalent, right? And notice certainty equivalent is below the expected value. The expected value is V. The certainty equivalent, when you have risk aversion, is going to be something below the expected value, right? And this shows you, so the idea is if we were trying to decide, for example, suppose we were trying to decide we had a option that we had this possible course of action. The other course of action was going to guarantee us something between C and V. Well, if it was going to guarantee something between C and V, we would choose the certain course of action, because the certainty equivalent of our first course of action is only C. Therefore, if you can guarantee us something greater than C, then we would choose option B or option 2. But if the other course of action has a certain net benefit less than C, then we would choose the gamble, which is course of action 1 right here. So again, the certainty equivalent allows us to compare it to other courses of action, either other courses of action that have no uncertainty, or if other courses of action also had uncertainty, we would calculate their certainty equivalent, and we compare certainty equivalent to decide, which one is best. So that's sort of graphically, but let me just go through the steps. How do we actually use certainty equivalents to compare courses of action? Well, the first thing we do is we formulate an appropriate utility function based on the degree of risk aversion, right? What's the utility function based that sort of captures the relative risk aversion? Then we calculate the expected utility for each course of action based on the net present value or net benefits and the utility function. Then for each course of action, we calculate the certainty equivalent, right? So once we get the utility, we find the certain net present value or certain net benefits that give the same expected utility. And then finally select the course of action with the highest certainty equivalent. So let's apply that to our example of the Army communication systems. So this is the same, diagram as before. These are the net benefits from each system under each different atmospheric condition, the probability of those conditions. Applying the steps. The first step is formulate an appropriate utility function based on the degree of risk aversion. Well, let's go ahead and just use the risk-averse utility function from before. So the utility net benefits are the square root of those net benefits, or net benefits to the 1/2. Then calculate the expected utility for each course of action based on the net present value or net benefits and the utility function. Well, we already did that, right? We calculated the expected utility. We multiplied, again, the probability of each outcome times the utility. In other words, net benefits to the 1/2 raised to the power of 1/2 for under each scenario. And so we calculated the expected utility of each of the outcomes. Now, the third step is for each course of action, calculate the certainty equivalent, right? The certain NPV that gives the same expected utility. So to do that, right, we have the expected utility of each of them. So how do we figure out which certain outcome will give the same expected utility? Well, the idea is that we want to find a certain outcome whose utility is equal to the expected utility of that system. So system SX, right? S1, S2, S3, whatever it is, right? We want to, for example, have that the expected utility, I'll use system 1. Expected utility of system 1, we want to find some certainty equivalent such that the expected utility of system 1 is equal to the utility of the certainty equivalent. Now, its expected utility comes up when there's uncertainty. The certainty equivalent is a certain outcome. So therefore, which certain outcome has the same utility as expected utility of my uncertain outcome, right? Well, we know what the utility function is. The utility function is simply you take your net benefits and take the square root. So we're basically saying that given the expected utility of each system, which we have on this previous slide, right here, 9.39, 9.14, 8.30, what certain value would generate that same utility? And since utility is simply the square root of the net benefits, the idea is what certainty equivalent, when raised to the power of 1/2, or take the square root of it, gives you that value. So, for example, for the expected utility of system 1 was 9.339. So, what certainty equivalent, what certain value, guaranteed sort of net benefit, generates a utility of 9.39? Well, it means that you have the square root of this certainty equivalent must be 9.39. Therefore, 9.39 squared must be equal to the certainty equivalent, right? Certainty equivalent must be, you square each side, it must be 9.39. So 9.39 squared is 8.17. So the certainty equivalent for system 1 is 88.17. A certain net benefit 88.17 would be equivalent to the uncertain different possible net benefits that you get under system 1. Same for system 2, and do the same for system 3. For each of them, you can find the certain value that yields a utility equal to the expected utility of that system. Then the fourth step is simply to select the course of action with the highest certainty equivalent. Now, so certainty equivalent of 1 is 88.17, certainty equivalent 2 is 83.54, certainty equivalent 3 is 68.98. Well, clearly, the certainty equivalent, the system 1 has the highest certainty equivalent. And so with uncertainty, with risk aversion, we choose system 1. Now remember, in the risk neutral case, we did not worry about risk aversion. We did not worry about utilities, expected utilities. We worried about the values. We did not have a risk premium or did not have a coefficient of risk aversion. And we looked at expected values and we chose system 3. But we made the opposite choice. System 3 rated the lowest once we considered the incorporated risk aversion and the fact that system 3 didn't perform very well in mild or severe conditions. So in fact both system 2 and 3 are penalized for poor performance with mild or severe storms. Now note, however, that you may get a different answer if you did this again with utility net benefits instead of having the z equal to 1/2, if z equals 0.75, z equals 0.25, there was different levels of risk aversion, right? Z equal 0.75, you'd be less risk averse. So you would punish systems 2 and 3 less if you had a 0.75 as your coefficient of risk aversion. And so maybe you would end up choosing, I haven't done the math, maybe you would end up choosing, for example, in system 2. But again, this shows you how you can use certainty equivalence to compare different outcomes. Now you might say the question, hey, professor, why did we do certainty equivalence? We got these numbers here, but utilities, without doing certainty equivalence. We did that in the last section, and we saw that we chose system 1. So why go through this again just to confirm our same results? Well, the answer is that this was convenient because all of them had the same potential scenarios. Each of them faced a 60% chance of normal conditions, 30% chance of mild conditions, and a 10% chance of severe storm conditions, right? And so when you do if you did the expected utilities, it's easy to calculate expected utilities, and therefore easy to compare them on the same basis. The problem, of course, right, is that what if you have you're comparing different things that have different, they're completely different. One has a 60% chance of, maybe one has 3 possible net benefits, one has 2 different net benefits, one only has 1 possible net benefit. I mean, you have all different types of uncertainty associated with each outcome. The most robust way to make the comparisons is to make sure you're making apples to apples comparison, is to calculate a certainty equivalent for each of the uncertain courses of action. Okay? All right, so that's it for the dealing with uncertainty cost-benefit analysis. What we talked about was, first, the ubiquity of uncertainty, the fact that uncertainty is unavoidable for the most part in cost-benefit analysis. We then talked about the most basic notion in uncertainty, which is expected value, right? When you have an uncertain outcome, the very first thing you do is you think about expected value. And as long as you're risk neutral, that captures, the picture. And we then talked about sometimes to do expected values, helps to do probability distribution. And particularly when you've got multiple possible outcomes, right? And you've got many different possible outcomes. It's easier to identify the probability distribution before you do the expected value. I mean, to some sense, you always have to do that whether you know you're doing it or not. In order to calculate expected value, you always got to calculate the probability. Not only to identify all the possible different outcomes, you got to identify the probability of each one of those. And then in this second part of the recorded, video, we talked about risk aversion. Right, now we introduced the idea of, well, what about when we don't necessarily try to maximize expected value, instead we maximize expected utility. And because we are risk averse. What does it mean to be risk averse? How do we adjust for risk aversion? And then lastly, we took that to the idea of certainty equivalence. When you have risk aversion, when you have uncertain courses of action or courses of action which have uncertain net benefits, right? And you want to compare them apples to apples. You want to make a common comparison. What you need to do is find the certainty equivalent for the net benefits or the expected net benefits for each of those outcomes or each of the courses of action, right? And then you can actually compare them on that basis. Right? So that's it. This is our week 3 asynchronous lecture. Our week 4 asynchronous lecture is actually going to be recorded. I'll put it up, certainly by the start of next week, but hopefully sooner. And it will be on monetizing non-monetary impacts. And it will be, so I encourage you to look at that early in the week because our next and last live Collaborate session will be next Thursday, in which we will talk about incorporating sort of the non-monetizable. What if things don't, the next lecture is about how do you take things that you think you can't monetize and monetize them, put them in dollar terms. But then what are the things you still can't put in dollar terms? How do you incorporate those in cost-benefit analysis? We're going to do that in the last day. I'd like to do apply it to some Army case studies, but I was just looking over the material, and there's a lot of material for that day, and so I'm not sure how much time we'll have or what I can give you in advance, etc. Anyway, the point is, this lecture and the next one are going to be ones you can download asynchronously, and I will see you again on, actually, is it a week from, so today, so it'll be the 23rd, is that right? Yeah, I think it's the 23rd. Well, Thursday. You know, the week 4 Thursday will be our last live Collaborate session. I'll see you then. But you have this lecture as well as another asynchronous lecture to download and watch before then. Thank you.